Hello, we are here for one more lesson of this T-FLEX analysis training course, and the topic for today will be the restraints. First of all, the location to specify a restraint can be any kind of element, so you can use a face, you can use an edge or vertex, so it's independent, and according to this type of element that you choose, for sure the software will consider different calculations. We have several types of restraints inside T-FLEX, and we consider four major types, which we will see in this video. The concept of restraint is to add this specific element to the body or to the bodies of the active study that we create. And the restraint, as the name says, will take out of the solid or the solids considered, will take out degrees of freedom of the solid. So to show you a couple of examples, I've created two simple elements, two boxes, and now I go to analysis. We will create a new study. I will consider all the elements here, and okay, here I will decrease a little the number of or the size of the mesh. So let's create a mesh. Okay, done. I will apply a force. We can do, okay, no big deal. We can do a force here, and I will give a big value. Okay, 10,000 newtons. Okay. And now, in terms of the restraints, we have the first one that we can open. We have the first one called the full restraint. And this type of element of boundary condition locks all degrees of freedom for the selected object or objects in this particular case. So again, you can apply this either to a face or an edge or a vertex, okay? And this will influence the results. So we can apply full restraint, and we can say, for example, this face, and it will create this kind of symbol saying that these elements in here will not move, okay? Will not move, neither translations, neither rotations. This is the meaning of full restraint. Then we have another kind of, and we can use them. I did not do it, but in fact, we can, it was my mistake, but we can use them to create a calculation to see the result and then see the other elements. So results, displacement, magnitude. So we can see that this area everything is fixed, does not move, and under the conditions that we've defined, the movement is somewhere else. So take this out. Okay, done. So now we go to partial restraints. I've gone back and took the mesh out and the study out. Let's create them again. Sorry for my mistake. So again, in the same step, partial restraint. Partial restraint. We can define this partial restraint in different degrees of freedom. Anyway, when we define this partial restraint, we need to ensure that the numbers of restraints to fix the model are enough. Okay. The idea, for example, we can use, I did not mention, but it's the same. We can use also an edge, a face, or a vertex. So we can go into partial restraint and we can say, for example, in this face here, and we see the global coordinate system and we can use it. I can lock it only under the X direction, okay, and on the other directions the system can move. This is the kind of idea that we can apply when we are working with partial restraints. But another important topic about this is that we can use several types of coordinate systems. Okay, we can use the orthogonal, which is the basic one. We can use the cylindrical or the spherical, and according to the systems that we use, we can restrain the elements in different ways. The principle is the same. We apply conditions, and according to what we say or to what we set, the element or the elements will take degrees of freedom out. The idea of having a local coordinate system instead of the global one is that a local coordinate system is used to bind this coordinate system together with the model, and it makes a difference because it also the location of the coordinate system is also different. So in terms of these boxes, independently of what we want, when we mention, for example, this selected in x axis, it means that it's fully constrained in this direction and the value should be 0. Or we can apply a value and it will be constrained but with a known displacement, so it's the same. If there is no flag, it means it has no restraint in this axis or in this condition that according to what we saw, it can be other, like in cylindrical coordinate systems, by radius or by circle or by the rotation axis. I invite you to see the theoretical course because we have some graphics and some drawings explaining exactly all of these things. Okay. So basically, considering these three conditions, we have these different possibilities. Then we have, and I will go back, then we have another kind of restraint called the contact. This contact, I will activate it, is needed. These kind of restraints are needed in studies where we have contact bodies, and when I've created these two elements, it was also thinking about these bodies, these contact possibilities. We have 4 types of contacts that are possible to study. Okay, so I'm defining a restraint contact. So I will say that the contact faces are this one, and in the contact type we have these 4 types. The first one is called the rigid contact, and it's used when it is necessary to bound the contact surfaces of the bodies inside the study. So there is even that the materials can be defined with different for each of the elements. The idea is that there is no deformation between the materials. So if I say rigid contact and I say this face as the common one, so I will confirm, you get this kind of graphic here, and let us solve to see what happened. I forgot to define, so I will say full restraint, not in this face, sorry. I will say in this face here and in this face here, and now solve it, and we'll get the solution now. And also because I went back, I did not define the force that I will give as 10,000 newtons again. So let us solve it again. Okay, and now we should have a deformation, but they should deform together. Okay, as you can see, no deformation between them. Let us go to restraints. Okay, this one here. Now we can change the type of restraint. We can say, for example, no contact. And the no contact is a little different because the surfaces can freely move with respect to each other. So they can be penetrated inside one another. So let us try to make a new calculation and see the difference that will happen. As you can see, you see there is penetration from the top solid to the lower one because they are not anymore acting together. This is another type of partial restraint, of contact restraint with no contact on the definition. There is one other restraint called the tangency, and the tangency it is interesting because in this particular case it will make a kind of a slide between the elements. So it bans the mutual penetration and it allows that this physical phenomenon of sliding to one another occurs. So it's interesting also because we can simulate something like what we are going to see. There's some interaction, so it will take a little more time. Okay, let us try to simulate the result. Sorry, my mistake. I put it solving again and I want to show you the results. Let us wait a couple of seconds more. Now, to avoid a mistake, so we have this kind. You see that they have a rigid contact and they are sliding one another, which is also a very interesting kind of study. Finally, in terms of this kind of restraint, we have something called the rigid wall, and the rigid wall is used to model a contact of a body with a rigid surface whose deformation can be neglected for the modeling purposes. In this particular case, we need to define what is the surface that is rigid. So I must go back. Let's go back and take this out. So in here, contact, and this guy, sorry, rigid wall. And I can say that the faces can be, for example, this one here. I'm not sure if we are able to see exactly a visible result, but let's try. Let's try to create a calculation and see what is the result. So results, okay, quite different. So you see the lower surface, it is rigid, so the system applies all the defined conditions, and we are smashing the element on top because below there is no deformation. Finally, so let me take the restraints out, taking this out and the other one also out. So restraints out, and I will leave the results. Finally, in terms of the restraints, we have something called the additional stiffness, and this type of restraint allows us to define an elastic interaction, additional stiffness, on the boundary of a body. So this stiffness is used when we are modeling the contact of a body with an external elastic medium, which is deformed together with the body. One example is the frame of a machine tool, which is deformed together with a foundation that is based on elastic damping elements, dampers. Also, a dam is supported by a bedrock, a railway, etc. And these can serve as examples of bodies connected with these elastic mediums. We can define, okay, so we can have also different coordinate systems again. And the stiffness type, it can be sum, it can be distributed according to what we give. So I will say distributed. I will mention this face here as the connection with the elastic medium, and I will say solve it. Probably will not see much difference, but okay, we don't have enough boundary conditions because I took also out this guy, and probably affected the calculation. So let us see the result. Probably not possible to see much difference. Okay, you see there is deformation with the medium. So this is another very nice possibility to create a restraint on the studied models. Just one detail. These stiffness types, which it is important. When we have this sum, this is used when the total stiffness of this elastic medium is known, and this value is uniformly distributed over the resultant area. In this particular case, we've defined a face or a length of an edge or whatever we have. So when this is distributed over these guys, when we have the distributed type, we use this when the specific stiffness of the foundation per unit area is known. Okay, so this is a detail, but it's important to get the proper results. So these were the topics that I had to show you, and it was important also to show results in these different cases applied to this system. I hope that the examples and what we mentioned in the video was clear enough to explain how to use the restraints. I think it is important for you to see all the videos that we are releasing with examples, and the other place where you can consult more information is the theoretical course, because inside we have more explanations, a couple more graphics also showing all of the things that we mentioned in the video. So besides all of this, any support that you may need, send us a contact, and we will give you all the necessary help.